Hello, everybody, and welcome to another thrilling session of notes that you guys are going to take. Make sure as we go through these notes that you have the guided note worksheet out and you're following along with that and answering those 10 questions. Good thing about the video notes is you can pause the video to write your stuff down so you don't have to worry about getting behind. So make sure you're pausing if you need to. And we're just going to jump right into it. We're looking at Earth's internal structure. We're now into our plate tectonics unit, and we're going to start from the inside of the Earth and work our way outward. So first thing we're going to look at is the heat of the interior of the Earth. And why is the Earth's interior hot? And it happens for basically two reasons, which we're going to cover today. And those two reasons are, number one, radioactive decay. So you have radioactive materials in the interior of the Earth that are decaying and putting out heat. And then we also have what we call the heat of formation, which we're going to go over both of those now. Oh yeah, we break down heat of formation into two different groups: gravitational collapse and then constant bombardment. Okay, so first is radioactive decay. About 50% or half of our heat we think comes from the decay of radioactive materials. This is kind of a newer concept in geology. Over the last 10-15 years, this has become much more of a prevalent idea that these radioactive materials are in the core of the Earth, and the process of them decaying is releasing energy, providing that heat. So when we look at radioactive decay, we're mostly talking about uranium, and it's not just a simple decay. If you look at this slide, there's a bunch of steps when they lose what we call alpha particles and beta particles. And you have this unstable element that is going to decay until it becomes stable. And during each of those steps, as it decays, it will release energy. That's about as deep as we're going to go into it, since we get to do this all over the video. We're going to skip over this stuff. So one thing we look at and how we understand how old elements are and things like that is through what we call a half-life. A half-life is basically how long it takes for a radioactive substance to decay halfway. So like if we look at those blue boxes that we have over on the left-hand side, that would be like our sample of uranium. So right now we have 100% uranium. None of it has decayed into lead, so that Pb206 is lead when it becomes stable, and so we have no ratio. But after its first half-life, that's when the probability of, in this amount of time, half of your sample will have decayed. So after its first half-life, you have half of it is uranium, half of it is lead. It's a 1-to-1 ratio. And then after its second half-life, then we only look at the remaining uranium. So we lose half of that remaining uranium. So then from our total sample, we have 25% is uranium and 75% becomes lead. Then if we go to a third half-life, we're only looking at the remaining uranium again. So we cut that 25 in half, and we get 12.5 and 87.5 to a 1-to-7 ratio. So that's how half-life works when we're trying to figure this stuff out. Okay, and then the next way that we got heat in the interior of the Earth is by what we call the heat of formation, which is exactly what it sounds like. It's the heat that was generated when the Earth was forming. So the very early stages of the Earth, think back to what you learned about during nebular theory, how we had all this accretion and stuff hitting the Earth to create the Earth, and that also created heat. So all of those rocks hitting the planet is generating that heat, and that kept basically the whole planet molten. It was basically a liquid ball of molten lava for the early stages of the Earth. And then as the bombardment slowed down, the crust developed, and it basically acted like a big insulator, and kept all that heat in the interior. And then the other part of that is what we call gravitational collapse. Um, so as this interior, the whole Earth was a molten hot ball. It was um, like the densities had not mixed out yet. And so that started to happen because it was all liquid. So gravity caused the heavy, more dense materials to get pulled towards the center, and then the less dense materials started to move out towards the surface, and then that friction of the movement created heat, and then once again when the crust formed, it trapped that heat in. Okay, so that's where the heat comes from, and then that's how we got the layers as we know them today. So we're actually going to learn about the layers like you've learned since elementary school days, and then in another assignment you're going to learn about the way we reclassify the interior of the Earth based on physical properties, in a different assignment. So these ones are mostly on chemical composition, which are the layers that you've known basically since elementary school. So if we start at the very top, we've got the crust, mantle, outer core, and inner core. And we're going to just really briefly look at these. We're not going to go too far in depth into them because you've learned about them for so long. We do want to pay one specific focus on the mantle, though. So really the crust is our very thin layer on the outer. It's 3 to 25 miles thick, and it's a lot cooler than the rest of it. And then the important part for us as we move forward with this unit is the crust is broken up into tectonic plates. All right, and then the mantle becomes a lot thicker. So it's underneath the crust. It's 1,800 miles thick. It gets a lot warmer, up to 4,000 degrees. And our important part is the mantle is this term that we call plastic. It's kind of like modeling clay. So it's a solid, but it can flow slightly due to the heat and the pressure that's there. This is where you may have been lied to by your elementary teachers back in the day when they told you that the mantle was liquid. It's easier when you're a little kid to understand the flow of the mantle when you know that it's liquid, but it's not actually a liquid. It's actually this plastic solid. So it's more like a solid, but it still has a slight ability to move, and that allows the convection to drive our crust movement. Okay, so the plasticity is the reason our plates on top are able to move. Okay, and then we've got the outer core, so now we're going below the mantle. Our outer core is a liquid, so it's a really hot liquid, nickel and iron mostly. And because it's this hot liquid spinning ball of magnetic material, it actually, it's not on there, but it actually creates the Earth's magnetic field. Okay, and then the inner core is at the center of the Earth. We're getting really hot, 9,000 degrees, but now the pressure is so high that it's forced back into a solid. So because there's so much pressure, everything pushing down on it actually becomes a solid again. Okay, and then the last bit for these notes is just how we get our evidence of the interior of the Earth, because we don't actually have the ability to get physical evidence of this. We can't go to the interior of the Earth. We can't even make it to the mantle. And so the way we think we know what the interior of the Earth looks like happens when we track the waves from an earthquake. So we have primary and secondary waves coming from an earthquake, and they can move through the Earth. And if we track their motion, that allows us to figure out what the interior of the Earth looks like. So if you look at the black lines on there, those S waves, you notice that when they hit the outer core, those waves stop. And what we know about the properties of an S wave is they do not have the ability to move through liquids. And so you notice that they do move through the crust and the mantle. So we know that those two are solids, but then it hits the outer core and those waves get stopped. And so that informs us that the outer core is likely a liquid. And then if we look at the yellow lines, the primary waves, they continue to move through the outer core and the inner core, but we notice when they hit those layers, they bend a little bit, or our science word for waves bending, they refract. And so they refract because they hit layers of different densities, and those different densities cause refraction to happen, and that creates those shadow zones. And so if we track those waves, that can tell us what those different layers are. Okay, that's the end of the notes.